Welcome to AI for Good, the leading action-oriented global and inclusive United Nations platform on AI. Organized by ITU in partnership with 40 UN sister organizations and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end, as we will hold a 30-minute networking session in the neural network. Here you can meet, ask questions to our distinguished speakers, connect, and chat with the AI for Good community. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Thank you very much, Anna, for the introduction. A very good day to everyone, and thank you so much for joining today's session. Welcome to the AI for Good Machine Learning 5G Challenge webinar session. My name is Thomas Baskor from the ITU, and it is my pleasure to introduce the session. The Machine Learning 5G Challenge aims to create a community to solve network-related problems using AI and machine learning. Today, we are very excited to host yet another interesting webinar for the Graph Neural Networking Challenge 2022, which is titled Improving Network Digital Twins Through Data-centric AI. As always, we are counting on you, our participants, to create an engaging discussion. If you have questions, please type them in the video and we will take them during the Q&A session after the talk. Without further ado, I would like to introduce today's speaker. Today's talk is going to be given by Jose Suarez Varela, a postdoctoral researcher at the Barcelona Neural Networking Center. Jose holds a PhD in computer science from University Polytechnic of Catalonia in 2020. He is the main organizer of the Graph Neural Networking Challenge since 2020-2021. Now, this is the third edition, 2022, of the Graph Neural Networking Challenge. He's also a principal investigator of EU-funded project Ignition. His main research interests are in the field of artificial intelligence for network control and management, traffic measurement, and cybersecurity. And in today's talk, he will introduce the Graph Neural Networking Challenge 2022 with the title, as already talked about it in the beginning, Improving Network Digital Twins Through Data-centric AI. And for this problem, participants will be given a state-of-the-art GNN model for network performance evaluation and an accurate packet-level network simulator to generate training datasets. And the participants will be tasked with producing or producing a training dataset that results in a better performance of the target GNN model. But also we have some goodies lined up for our participants. We have an important announcement that we are going to make at the end of the webinar. So now I would like to welcome Jose. Hello, Jose, and good afternoon.
Hello, good day. Thank you for inviting me to do this webinar, and thank you to all the people attending this session. So, okay, so can you see my slides?
Yes, thanks.
Okay, so thank you, Thomas. As you said, today I will present the third edition of the Graph Neural Networking Challenge for this year, which is entitled Improving Network Digital Twins Through Data-centric AI. So here you have the link to the website. Well, I will introduce some concepts around this new edition. So first of all, I would like to briefly talk about the Graph Neural Networking Challenge. This is a series of annual competitions on graph neural networks applied to networking that we are hosting at the Barcelona Neural Networking Center. So in each edition, we brought a fundamental challenge of graph neural networks applied to communication networks. So far, we have celebrated 2 editions. And in general, I would like to highlight that graph neural networks are becoming more and more popular in the networking field, and it represents the first and the only competition nowadays on GNNs applied to the networking field. Well, as you already know, this is organized as part of the ITU AI ML in 5G challenge. So this competition hosts several different problem statements, and one of them is the Graph Neural Networking Challenge. So at this point, I would like to especially thank Thomas Pasicolo, Vishnu Ram, which are today here, and Reinhard Skoll from the ITU, because they did a really good job to make this event more and more popular. So thank you very much. We really appreciate it. They help us to make this a large and a very popular event. So, as I said, the promise statement for this year will be entitled Improving Network Digital Twins Through Data-centric AI. So there are two main concepts here, which are the network digital twin and then data-centric AI. So I would like to delve into these two main topics. So what is a network digital twin? Well, digital twins are becoming very popular nowadays in the industry in many different fields. And basically, they refer to the realization of virtual replicas or digital models of physical objects or processes. So here you have an example of what would be a digital twin of a plane, for example. In this case, this digital twin would permit to simulate the behavior of the plane under some input conditions. So, for example, it could be used to answer questions such as what would happen to the plane if it had a specific failure, for example, in the electrical system, or what would happen if we had a new wing design in this plane. Okay, so in an analogy to the previous model, network digital twin refers to a virtual replica of a physical network infrastructure. So the idea is to have an accurate model of physical network infrastructures and be able to reproduce the behavior of that network infrastructure under some what-if scenarios. So we could answer questions such as, what would happen to the network if I change some configuration, or what would happen if there is a random failure in the network? In general, network digital twins can be applied to many fundamental networking applications, as we have accurate models of the network, so we can use them, for example, for network optimization or what-if analysis. So if a network operator wants to use a digital twin, for example, it can leverage it to know what would happen if they reroute the traffic on another path. So for example, for traffic engineering optimization, or also to check if they can support a new service level agreements with the current resources. Or, for example, in the case of network planning, to find what is the best network upgrade under some limited budget. Or in the case of troubleshooting, so imagine that this network operator detected a temporary service disruption that happened 2 days ago, and it affected some SLAs. So they can try to reproduce the state of the network at that time and try to figure out what was the root cause, ideally to find a way to prevent this failure in the future. So for example, adding some redundancy to the network. So in general, as I said, there are many opportunities for improving the control and management of networks with network digital twins. Related to this, we have recently published a position paper. It's now on arXiv, and it discusses some open challenges and opportunities within this field. Okay, so at this point, some of you might think, is this really a new concept, a network digital twin? So what about all the existing literature on network modeling? So There are many works from the 80s and 90s on analytical models. So, for example, based on king theory. And also we have accurate network simulators. So indeed, I would say network digital twins can be referred to as a renovated concept of those classical network modeling techniques that has the ambition of achieving more accurate digital replicas of the networks that can operate in real time. So if we look at traditional modeling techniques, analytical models are very fast, but they are sometimes inaccurate under real-world traffic conditions and with considering the physical effects or the impact of hardware in the network. And if we look at network simulators, they are more accurate, but at the same time, they are computationally very costly. So it's difficult to run them in real time. So in this sense, machine learning is a promising technique for building data-driven network models that can be both accurate and lightweight. So we can achieve a real-time operation. Okay, so I would like to discuss how can we build a machine learning-based network digital twin. If I were a vendor and I wanted to produce a network digital twin product, what I would do is to generate this product in a networking lab. And in this lab, there would be two main components, which are a network testbed, where we can generate some data, and a machine learning models that will be trained to finally produce the network digital twin product. So the idea is that in this network testbed, we can generate different configurations, we can inject different traffic distributions and take some measurements so that we can finally generate some samples that will be used for the machine learning model. So after training this machine learning model, the network digital twin product should be ready to be directly deployed in customer networks. So here, there is a fundamental aspect is that network digital twins cannot be trained with data from real networks if they are based on machine learning techniques, as it would require to cover edge cases like generating high congestion scenarios or even considering potential failures that can happen at runtime. So if we don't add this kind of samples, then the machine learning model probably won't make good predictions if they happen. So one important point here is that we need machine learning models that can generalize effectively to samples from other networks that were not directly seen during training. Meaning that we can, after generating the data set in the networking lab, we can train the model, and the model should be able to generalize to different network topologies with different configurations and different traffic patterns. So here I would like to highlight that generalization is an essential aspect for this kind of machine learning based network digital twins. Okay, so let's go into the vendor's lab. So how the vendors produces this machine learning based network digital twin product? Well, as I said, we have two main components, which are the machine learning model and the data set used to train that machine learning model. So regarding the machine learning model, as I said, we need machine learning based techniques that have a strong generalization capabilities over network related data. And indeed, during the first edition of the Graph Neural Networking Challenge, we have focused on building robust graph neural network architectures that can effectively generalize over networks. So as an outcome, GNNs have already shown strong generalization capabilities over many different fundamental networking parameters. So we have shown that GNNs are able to scale to much larger networks than those that were seen during training. We have shown that they are able to generalize to different routing and queue scheduling policies. And we have also shown that they are able to generalize to different traffic models and traffic matrices. So the main reason behind the success of graph neural networks in communication networks is that in general, networks comprise much relational information at very different components, like the topology, the routing configuration, the user connections, signal interference, interdependencies between flows. So mathematically, all this relational information is naturally represented in the form of graphs. So here you can see an example where we have a network scenario with topology, routing, and other components such as the routers, links. So this information can be naturally represented in the form of heterogeneous graphs, typically. And that's what we did during the last 2 editions of the Graph Neural Networking Challenge. So here it's important to understand that GNN is nowadays the most suitable machine learning technique nowadays to process, model, and generalize over this graph structure data. So we can consider that so far GNNs have demonstrated good potential to generate accurate digital replicas of the network. And as an example, I would like to share with you some evaluation results that we presented recently at the IEEE Infocom conference this year. So we presented a model called RouteNet Erlang, which is an extended version of a previous model called RouteNet that we proposed some years ago. So in this case, we trained the model with different topologies, different routing queue scheduling policies, and also different traffic models. So including on-off distributions, constant bit rate, and autocorrelated traffic time series. And we evaluated the model in samples from a different network, which was the German backbone network that you can see here. Particularly, we evaluated it over 50,000 samples that were not seen, of course, during the training. And we compared the results in terms of relative error when predicting the per path mean delay. So as a benchmark, we used a state-of-the-art queuing theory model. And what we could see here, you have the results. We have a cumulative distribution function of the results. So basically, we could see that the RouteNet Erlang model could achieve a relative error on average around 3%, while the queuing theory benchmark obtained around 35%. And what is more important is that if we look at other performance metrics, such as jitter or the packet loss, the queuing theory benchmark performed quite worse. So, for example, for the case of jitter, the queuing theory benchmark obtained a relative error around 69%, while the GNN-based model, RouteNet Erlang, achieved around 11%. So this showed that we can predict accurately this kind of performance metrics with limited execution time if we compare it to accurate network simulators. Okay, so going back to the scenario at the vendor's networking lab, I would like to discuss a bit about the generation of the dataset. Well, one main observation is that there's no public research nowadays on how to produce good datasets for machine learning applied to networking. And from our previous experience in the previous editions of the challenge, we know that generating a good data set requires many different aspects that are very relevant, such as having domain expert knowledge. So understand what are the relevant features to the machine learning model in a particular networking problem, or having a good coverage of possible cases. So for example, covering different congestion levels in the network. Also, as I mentioned previously, considered edge cases. So for example, some potential failures in the network. Also, when simulating networks, it's important to avoid an ambiguous labels. So for example, if we train or if we simulate a network from scratch, there is a part that shows a transient behavior. So we need to go or to detect the part that is in the stationary state. So we can avoid some noise on the performance measurements taken from the testbed or the simulator. And finally, it's important also to take into account the cost to produce these data sets. So we need to try to reduce as much as possible the number of samples, as usually each sample takes much time, cost, and computational power to be obtained. So in previous editions, we generated the datasets with network simulators, and our network engineer in our group, in the Barcelona Networking Center, struggled to create these datasets to have a good coverage of relevant cases. So the datasets that we released had around 100,000 between 100,000 and 400,000 training samples. And we needed to run them in our computing cluster, and it was quite computationally costly. So the main motivation after these two editions is that we would like to encourage the networking community to explore the data-centric AI approach for machine learning applied to networking. The potential benefits that we believe it can have is that we can achieve larger performance gains. So nowadays we have good graph neural network architectures that can effectively model networks, but we need good data to train those models. So it's important to have a better coverage of important training samples, and this will enable to achieve better performance. And at the same time, it's important to account for the cost to generate those data sets. So if we are able to identify what are the most relevant training samples, we can reduce the cost to generate those data sets by only generating this reduced set of samples. Indeed, data-centric AI is becoming a very hot topic in the machine learning field. There are many industrial applications that are gaining more and more interest on data-centric AI. Probably some of you know the data-centric AI competition that was celebrated last year, and it was organized by Andrew Ng, which is an AI evangelist from Stanford. So in this competition, they proposed a similar challenge on data-centric AI, but they applied to computer vision. Particularly, they applied it to the popular problem of classifying handwritten digits. And one important aspect here is that by following the data-centric AI approach, we think that it's very important to have also expert knowledge on the field. So we need specifically to attract or to generate knowledge for data-centric AI applied to networking. So that's the main objective of this challenge. Okay, so now I would like to briefly outline how will be the problem statement of this edition. I will provide some details and also some logistics about this edition. So in this year, we will provide to participants a state-of-the-art GNN model for performance evaluation. So this model will be implemented by a graph neural network, and it will be something like the scheme that you can see here in the slide. So it will have as an input network state description that will include network topology, some configuration parameters like the routing or the queue scheduling policy, and also a description of the traffic in the network, including different traffic models and the average traffic volume on each path. So with this input, the GNN model should be able to reproduce the behavior of the network and finally produce estimates of the per path mean delay. Okay, so in this context, we will ask participants to generate the best dataset to train that GNN model that we will release at the beginning of the challenge. So this training dataset should have some samples, and particularly samples should have as input network topology, routing and queue scheduling configurations, and the traffic matrix, including different traffic parameters such as the model and the traffic intensity. And to generate this dataset, we will provide a discrete event network simulator that is based on the popular Omnet++ discrete event simulator. So we will provide a Docker image that already implements this simulator, and that we hope it can be much easier for participants to generate the training dataset. Okay, so here, as I said, it's important to take into account that simulators are very costly. So we have scaled down the whole problem in order to enable the generation of the dataset on commodity hardware. So the idea is that any participant can easily generate the training datasets with our network simulator in less than 1 hour on commodity hardware. Also, at the beginning of the challenge, we will provide a validation dataset. So participants can use this dataset to evaluate the performance of their solutions in this dataset. Particularly, it will contain samples in networks up to 300 nodes, which are considered large in the context of this competition. And we will ask participants to generate training datasets that should comply with some constraints. So with the network simulator that we will provide, participants should generate training datasets that should have a maximum of 100 samples. So it is a very limited dataset if you compare it with the datasets of the previous editions. I recall that they had in the order of hundreds of thousands of samples. And also, another constraint is that samples must be from networks up to 10 nodes. So these are considered very small networks within this context. So the idea here is that with these 100 samples, they can train the GNN model, and the GNN model should effectively generalize to the larger networks up to 300 nodes. Participants will be able to train with this training dataset the GNN model in less than 1 hour. So it will take around 1 hour to generate the training dataset and another 1 hour to train the GNN model. Okay, so in the end, what we should achieve with the training dataset is that it should be designed to help the GNN model to generalize to larger topologies, which can include larger link capacities and larger traffic aggregates that were not seen during the training, and also different routing and queue scheduling policies and traffic load levels. So by the end of the competition, which will be at the beginning of October, we will evaluate the solutions of participants on a test dataset. And this test dataset will follow similar distribution to the validation dataset that was already released at the beginning of the competition. So this evaluation phase will last around 15 days and will be made automatically in our evaluation platform. And the idea is that participants will train the GNN model with their training datasets, and we will evaluate the prediction accuracy of those trained GNN models on the test dataset. And a good point is that, as in previous editions, participants will be able to see a ranking in real time with the accuracy or with the final scores, and compare to each other during this evaluation phase. So after the evaluation, we will post a provisional ranking with the scores of all teams, and we will ask only top 5 teams for their training datasets, the code to generate the datasets, and also a short report describing their solutions with around 1 to 3 pages. So we will reproduce and validate the training of these top 5 solutions to check that they comply with all the rules of the challenge. So mainly to check that they complied with the constraints in the training dataset. So maximum 100 samples and with samples in networks up to 10 nodes. Okay, so just before finishing, I would like to quickly summarize what are the main resources that we will provide. So first, we will provide a network simulator based on Omnet++, which will be embedded in a Docker image. We'll also provide a state-of-the-art GNN model for performance evaluation, and a validation dataset that participants can use to test the accuracy of the trained models. Also, we have prepared some Jupyter notebooks that should be helpful for participants to start working on the problem statement. So the idea is that by following these tutorials, they can execute the whole pipeline of the competition, of the challenge. Also, I would like to highlight that there will be support from the organizing team. So we have a mailing list for Q&A for participants, and we will actively follow it and answer all the questions. So you will have support to develop your own solutions. So the final outputs from participants will be the training datasets that they will submit, and also a description with the methods used to create those datasets. And eventually, the expected outcomes for this edition is that ideally, we will advance the state-of-the-art on how to produce good datasets for machine learning applied to networking. So in other words, we want to quick start the area of data-centric AI, particularly applied to the networking field. And well, here you have a tentative timeline of the competition. It can slightly change over the course of the competition, but basically, the registration is open from tomorrow in this prompt statement. So you can access the website, and you will be able to find a registration link there. All the tools and the validation dataset will be released by the end of June. So participants will be able to start working on the challenge by the end of June. As I said, after that, we will do an evaluation phase during the first 15 days of October. Then top 5 participants will submit their dataset, code, and documentation. And finally, we expect to make the official announcement of the winners around November 2022. So after that, the winners will access the ITU Grand Challenge finale. They should follow the guidelines of the general IT challenge. Okay, so that's all on my side. I hope you enjoyed the presentation, and I hope that I would like to encourage you to participate in this new edition of the Graph Neural Networking Challenge. So please, if you have any questions, don't hesitate to ask.
Thank you so much, Jose, for this interesting talk. This is a really different problem statement that we have been having, because in the first 2 years, we have been giving our participants data sets and asking them to create models, but now it's the other way around. So it's quite interesting to see this type of problem statement in our challenge. So now it's time for Q&A. I know some problems are already there in the chat. So I will invite my colleague Vishnu. Good evening.
Thanks, Thomas. And thanks, Jose. It's an excellent problem statement again. I want to remind the participants that Jose has been there for 3 years. This is the 3rd year that he's back, and it is a very popular problem statement. So please, I would really encourage participants to register and compete. I want to start with a question from Marco. You did mention, Jose, about the problems with the data sets. It's of course not possible to get all scenarios from real networks. So you need digital twins and you need simulators. But at the same time, the current data sets are having problems, right? So what is it that can we collect data from real networks? What kind of simulations are required? For example, in the Omnet++ that you mentioned, how are you addressing some of these problems with the data sets in the techniques that you mentioned?
Well, here I try to somehow summarize what is a good data set for us, at least from our previous experience. I think that there are many relevant points that we should take into account, and I think it also depends on the network application and the networking use case. Well, for example, in the case of performance evaluation, it's important to cover different operational scenarios and so on. So this is quite challenging. I think that obtaining data from real networks can be very useful. I think that indeed it can be complementary. So somehow another approach to generate the network digital twin could be to first train it with representative samples generated from controlled network testbeds, and these samples can include highly congested networks, can include failures, and so on. And then we can somehow fine-tune with data from real networks. So I think that this kind of data can be very useful, but it's difficult. It's hard for me to find a way to train a machine learning based network digital twin that can be exclusively trained with data from real network infrastructures or real world customer networks, let's say, in production.
So in the techniques that in this particular problem statement, you are asking to generate data sets. Is that for specific scenarios, or is that for a given scenario, or based on the baseline model that you provide?
Well, I think there is an important part here is that we should consider the model that we ask to train. So here we are providing participants a network digital twin for performance evaluation. So the inputs are the topology, configuration, and traffic, so including routing and queue scheduling policies. And the output are performance metrics. So in this case, is the per path mean delay. In general, this model can predict any performance metric at the granularity of paths. So it's important to consider also the inner workings of this model. We plan to provide a very detailed description of the model and also the code, because otherwise I think it's difficult to generate good samples that can help the model to then generalize to different network samples. So let me recall here that the idea is that the training dataset should have samples from networks up to 10 nodes. And this will help participants to generate training datasets with much limited cost. But then we will test the accuracy of the trained models in samples of networks up to 300 nodes. So they should be highly scalable. They should scale to larger link capacities, larger traffic aggregates. So this is quite challenging. I'm quite, I think that it's important to take into account the inner workings of the model to generate good data sets.
Thank you so much. I think we have also answered the question from Ifeijin. That is regarding exactly this, that what are the constraints under which this model has to be trained. I have one more question regarding your previous answer. How do you test the generalization? So you mentioned one part, which is the larger link capacities and traffic aggregates, basically scaling. But other than scaling, are there variable link capacities and topologies differences which you consider for generalization?
Well, we will generate, or in the validation dataset, we will have samples with topologies that are larger, with larger link capacities, but also they will have very different routing configurations with source destination routing schemes, and also different queue scheduling policies. So we can, on each node, we can select different policies with different number of queues. And also when generating the traffic can have different models. So following more varsity models, following constant bitrate models. So the model should generalize to all these traffic and configuration parameters as well.
I see. Yes, thank you so much. About real time, let me take this question from Klaus. He's asking about real time. Actually, it's an interesting question. I know we know that the training that we do is non-real time, but the inference part. How about the inference part? Could you talk about that a little bit? Whether in your experience, is the inference real time? How real time? And what are the latency considerations in your experience?
Well, that's a good point, because the definition of real time can be somehow subjective, right? But let me give some numbers. So, for example, when we apply this kind of graph neural network models to networks up to 300 nodes, they can make inference in the order of few milliseconds. And one can think, okay, maybe we need even faster models that can even make faster predictions, so we can use these predictions to operate the network in real time. But if we compare it with the state of the art, the most accurate technique, or the technique that has comparable accuracy to these machine learning based network digital twins are precisely the packet level simulators. So these simulators compute for each packet event the forwarding on nodes and so on. So their cost is proportional to the number of packets and also the number of the topology size. So from our experience, if you want to simulate a network of around 300 nodes, it can take even half an hour. So I think it's an important reduction in terms of execution cost, from few milliseconds to 3 or 30 minutes in simulator. So yeah.
Interesting. Okay. I believe it also, just to add to your answer, I believe it also depends upon where you apply the inference. At what point and where you apply the inference. If let's say you are trying to apply the inference in the real network to let's say to counter a security vulnerability or something like that, then probably it is latency critical. But if it is probably to optimize some configurations, then it's not so latency critical.
Yeah.
Anyways,
maybe
interesting question.
Yeah, maybe I'm focusing on the applications for performance evaluation. Yeah, you're right.
Yeah, very interesting.
I completely agree.
Yeah. There is a question from Jean. Can we consider the digital twin used in the challenge as a snapshot of a given physical network, or some other definition would be more accurate? Could you take that question and then we can discuss?
Well, more or less, it's a snapshot. So we can consider that we have some input network state defined by these 3 parameters that you have here in the slide. And the idea is that if we simulate these input conditions in for example, in a network simulator, and the network was previously empty, we should simulate the whole process. So we will have a transient part, and then we will have stationary part. So what we do is to consider only the stationary part, and we measure the performance metrics in this stationary part. So somehow we can consider it as a snapshot.
Okay. I just want to add to what Jean is asking. How about wireless links, and also how about mobility? Because when you add these two, the complexity kind of increases. I know that you're looking for generalization, but like he's asking, when you take a snapshot trying to look at both wired and wireless networks, especially when you add mobility, things get changed more rapidly. I guess that's the interesting point here. What are your views on that? Can such digital twins be applied for wireless links along with or without mobility? What are your views?
Well, that's a good question. I think that, as you said, wireless networks are much more dynamic. And somehow I think that there are many parameters that can be probabilistically defined. So, for example, you can probabilistically compute the power, the loss, and so on, the mobility as well. So I find it difficult that you can adapt to the instantaneous changes. I see that these kind of solutions can work more in more extended time spans, and we are talking about few milliseconds, okay? But maybe using this kind of probabilistic definitions can help to effectively apply to wireless networks.
Interesting. Yes, I believe this goes back to the previous question from Klaus. Whether you are trying millisecond, sub-millisecond, real time, or are you looking at more generalized version of trying to abstract such complexities into the level of detail that you have here. I think it is quite an interesting problem. Maybe some other time. There is a question from Marco. He's asking comparison results in terms of accuracy between GNN and packet level simulators, for especially, I guess he's asking for packet loss and latency. So, comparison in terms of accuracy, not convergence time between GNN and the packet level simulator. Do you have any comments?
Well, I presented as an example these results from the RoundNet Erlang model, which was presented at Infocom. Indeed, this CDF, this this probability distribution shows the relative error of the RoundNet Erlang model and the queuing theory model against a network simulator. So the ground truth here is a network simulator. So in terms of accuracy, here we are evaluating the model on different topologies with different routing and queue scheduling policies, and also considering a mix of traffic models. As I said, it includes constant bitrate, and it includes more varsity models, such as on-off distributions. What we can see here is that on average, the model achieved around 3% error with respect to the accurate packet level simulator.
I see.
Okay, and regarding I see that okay, he's also asking about jitter and packet loss. So what we could see experimentally in this evaluation is that in terms of jitter and packet loss, the queuing theory baseline worked quite worse than when we apply to delay. So in the case of delay, the queuing theory benchmark achieved around 35% of relative error. In the case of jitter, around 69%. It's important to consider here that we are applying varsity traffic models. Queuing theory is quite inaccurate when we have this kind of realistic traffic patterns.
Is that the only reason? Can you explain the huge benefit? I should say, no, huge. Yeah. So what is the reason? Is that the only difference, that queuing theory is not generic enough to adapt to such topologies?
Well, the main reason I would say is that it does not adapt to real-world traffic patterns like varsity traffic, but there are also some other components. So, for example, when you need to model real-world routing configurations and topologies, you need to model it as multi-queue to multi-queue systems, and it also introduces some inaccuracies. But I should say that experimentally, the parameter that makes queuing theory work worse is when you introduce varsity or more realistic in general traffic models. So, for example, if they are non-Poisson processes.
Interesting. Data collection. So there is a question on data collection. Isato is asking, data collected is huge. And well, I guess the question is on security vulnerability, but I want to ask you slightly variant of that about the variability in the data, right? Because it's not, as you say, the real network may have different types of topologies and different characteristics. So you may collect data from different types of networks, or even simulators for that matter, and you will say variation in the type of data which is collected. I guess the challenge is also about that, right? So I think, how do you deal with it, and the variation in the data which is collected? Is there some comment that you would like to make, especially with this challenge in the background? Is there some?
Okay, so yes, it's important also to understand where will we test the model, because the variability somehow is driven by the kind of scenarios that then you will see at runtime. No? So in our case, we generated a validation data set that is intentionally generated to cover many different cases, as I said, in larger networks, but also with some non-standard routing configurations, non-standard scheduling policies. So these are aspects that then we should take into account when generating the training data set. So we need to somehow predict what are the kind of scenarios that we can find in the real customer network if we are in a real use case, and try to produce cases or scenarios as similar as possible to those that then we can find. That's why I say that it's important to cover as much as possible all the limit cases, like for example failures or highly congested networks. This is something that usually doesn't happen in production in networks, but in case it happened, we need that these models should be very accurate, and especially in those scenarios, it should be very, very, very accurate.
Thank you. Could you talk about evaluation? So you do measure the accuracy. What else are you looking for in a winning solution? So I want to win. I'm a participant. I want to win. So what are the parameters? One is that it should generalize to large set of nodes, and two, it should be accurate when you test with such large set of nodes. Is there anything else that I should do?
Well, I think as I mentioned previously, probably I think that it's important to understand well how the GNN model works and how different traffic samples can affect to the GNN model. So ideally, what I would like to see are solutions that don't only generate network samples from the perspective of the network. No? So I will cover different congestion levels, I will cover different configurations, but also that are somehow based on the inner workings of the model. And of course, it can be complemented with many more generic data-centric AI techniques, such as cleaning well the data, filtering the data. So a good solution, I think that it can be very complete, and it needs expertise in machine learning and in networking.
Can I submit more than one data set?
Well, by the end of the competition, the idea is that we will make the evaluation phase, and it will the duration will be 15 days. So we will have a limit of submissions per team. There are, I think, they are 20 in total, 20 submissions in total, and a maximum of 5 per day.
Okay. And in the reference model that you are giving, do you also give its performance?
Well, we will give the validation data set, and it will be labeled, so participants can check the accuracy against this validation data set. We will also provide a training data set, a baseline training data set, and participants can train the model with this baseline training data set, and they can easily check what would be the accuracy of the model in the validation dataset. So the idea is that we will provide some Jupyter notebooks to make it very easy for participants, so they can just execute the whole Jupyter notebook, follow the pipeline, and use this initial dataset to check the solutions, so that they can then improve the training dataset and re-execute the whole pipeline.
But you do provide a model also, right, in the beginning?
Yeah, we will provide a model implementation, but not train. So we will provide only the model architecture, the code, and the training dataset to train this model.
And that includes no results from the model also, right?
Not directly, but in the tutorial, we will follow this path. We will make the whole pipeline to finally get them.
One last question: Do you want the participant to use any specific machine learning framework, PyTorch, TensorFlow, whatever?
Okay, that's a good point. So we will release the model in TensorFlow. So they will need TensorFlow, and for the network simulator, we will use Docker. So this is because the network simulator is often difficult to be installed and to be compiled and so on. So the idea is that by using a Docker image, they can easily install Docker and use the image and only interface with this image with one command. So.
Okay, thank you very much, Jose. Yeah, I think it's quite an exciting challenge. Thank you for answering all the questions very patiently. We are very excited to see the further question answers in the roundtables. Please, back to you, Thomas.
Thank you so much, Vishnu, for the Q&A session. At this point in time, I would like to thank Jose for the great session, for introducing the Graph Neural Networking Challenge 2022. We thank you so much. Coming back for the third year to be with us, to join us in the challenge. It's quite amazing to have you around. So thank you so much. As I already mentioned at the beginning, that we have some goodies. So I would like to make a brief announcement. So, okay, so what we're gonna do is that, okay, I'm gonna share my screen. One small announcement is that the opening of the challenge is soon, and Jose will be sharing the link to join this problem statement. You will find it also, we will share it on the challenge Slack, as well as on the challenge website. Now, to the main announcement. We are proud and happy to inform you that this year we have the state-of-the-art IT challenge compute platform. So this compute platform is going to be given to all participants of the challenge, especially those who have challenges to have good GPUs or good computers to perform their machine learning jobs. We don't have too many resources, but I think we have enough resources that we can share around. As Jose was pointing out, that for example, in this problem statement, for the training, after you get the data set, you can train it for roughly an hour. So if you have access to these GPUs, let's say we give you 2 hours or 4 hours, it should be enough for you to have a good solution. So we have free GPUs, 3 GPU access. You can have notebooks. You can create Jupyter notebooks, or you can use Python kernel. So this is the announcement, and we are happy that we can provide our participants with access to a good compute platform with GPUs. Okay, so this is the end of the announcement. Now, as we are about to close the session, I would like to inform you that we have more webinars. The next one is on Wednesday, where we introduce another problem statement for the challenge. So be on the lookout. But also there are more sessions on the AI for Good challenge website. You can visit the website and you can join all other sessions. If you want to view past sessions, you can log into the neural network and watch past sessions. So thank you so much, everyone. We are heading to the neural networking for some networking. So please don't log out. Let's chat on the neural network. Thank you so much and have a good day. Bye.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the satisfaction survey, connect with interesting profiles, or speak one-on-one using the chat and video function. After the 30-minute networking session, we invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits and poster boards, and build your personalized AI for Good program. It was a pleasure learning with you today. See you at the next AI for Good.